Okay, excuse me. Here we go with a lesson. This is thermodynamics part 4, and we're going to talk about what happens when the state is changing, so from liquid to gas, gas to solid, something like that, and how much heat is required. So, I think we've done a lab that was called the heating curve of water, and a lot of the times when we do this lab, we kind of only get this situation where it's ice water and it's heating up and then it gets to the point where it's boiling. But if we were to have a more controlled situation, we would see something like this. So our temperature here would be 0 degrees Celsius, and our temperature at boiling would be 100 degrees Celsius. And what happens is ice can be colder than 0 degrees. So we would have really cold ice, and as we applied heat, so as energy is added, as we apply heat, the ice would heat up and heat up and heat up and heat up until it got to 0 degrees Celsius. And then the interesting thing that happens, and hopefully we got to see this in the lab, but the interesting thing that happens is right here, this would be basically all ice and a little water. And as we move along this graph, it's more and more ice turning into water, more and more ice turning into water. And by the time we get to here, it's entirely water. So all the energy that's added from here to here doesn't change the temperature, it changes the state. So this is converting ice to water, and we can actually calculate how much energy is needed to do this. Once all the ice is melted and it's all water, when more energy is added, the temperature of the water increases. So this is pure water, and it's just water heating up. This is what we have experienced when we put a pot of water on the stove for coffee in the morning or whatever. Once it once it gets to 100 degrees Celsius, then it starts to boil. So boiling water stays at 100 degrees Celsius, and the more energy or heat you add, the more of the water boils away. And if we could capture that steam above the boiling pot of water, we would get to here and we would have all steam. And as we continue to add energy, the steam would increase in temperature. So we have talked about this, the specific heat of water, and how to calculate how much energy is needed to raise the temperature by a certain amount. And the same thing applies to steam and to ice. These have lower specific heats than water, but they're still really high relative to metals or something like that. So in this lesson, we're talking about this situation. How much energy is required to melt ice and turn it into water, or vice versa. How much energy is given off when water turns into ice, and this, how much energy is required to boil water, or vice versa. So let's take a look. Alright, so I think this is what I just said, but I'll repeat it. When a substance is changing from one state to another, heat goes in, so solid to liquid, what's this, melting, and liquid to gas, so this is evaporation, vaporization, boiling. Or energy comes out, so from liquid to a solid, so when water freezes, energy actually comes out of it. And condensation, when gas turns into a liquid, energy comes out. We can actually measure how much heat energy this is using. So instead of specific heat, so this is very similar to specific heat, but it is different. And frequently students kind of learn both at the same time and don't recognize that there's a difference between them. But heat of vaporization and heat of fusion. So heat of vaporization applies to this situation, heat of fusion applies to this situation, and just like specific heat, these are going to be some number that we multiply by the amount of substance that is changing. So our formula here looks really similar, alright? For specific heat, we had Q equals mc delta T, right? And again, this is not what we're talking about, but it is very similar. So if we take a look, we're talking about how much heat energy is necessary. We're talking about how much of the substance, so how much water or ice or whatever it is we're talking about, and then we have this coefficient, this number, that is a property of that substance. So this would be a property of water, just like specific heat is. And then change in temperature doesn't apply here because the temperature is not changing. We're just changing from one state to another. So we will work through an example where we use either this or this. So again, heat at fusion. Fusion, think melting. So fusion, think melting, freezing. And for vaporization, I think that one's maybe easier to remember. Heat of vaporization. You think vaporization, you got that. Or evaporation. Evaporation, condensation, boiling. I'm going to write all those. Condensation, boiling. Boiling. And remember, condensation, this is in switching from a gas to a liquid, so energy would go out. For these, energy goes in. These are just different ways of describing the same thing. Okay, liquid into gas. So, if we look at the units, for example, we have heat of fusion, so this is how we abbreviate that, or this is our variable. The units are in joules per kilogram, how much energy is required to melt a certain amount or mass of substance. And heat of vaporization, what happened, Torville? We don't know, but this is what I meant to write, joules per kilogram again. Alright, here goes our example. You've been watching for 7 minutes, good work. Here's our example. Our cup of water, so from the previous video lesson, has a mass of 500 grams, which you know is 0.5 kilograms. So as I'm reading through, I might be writing down the given information. I know the mass is 0.5 kilograms. It's at room temperature, so about 25 degrees Celsius. That's cool. So temperature, 25 degrees Celsius. Oh yeah, this question's a two-part. And we want to boil it all away. So that's two things that has to happen. First of all, we're going to raise the temperature up to 100 degrees. And then we're going to, the water is going to stay at 100 degrees, but we're going to boil it all away. How much heat energy is required to do this? So if we were actually looking at a heating curve, so energy, we would have this type of situation. The temperature starts at 25 degrees and it's going to go up to 100 degrees, and then it's going to stay at 100 degrees until it all boils away. So this is all water, and the water goes from 25 degrees Celsius up to 100 degrees Celsius. So to calculate this, we're going to be using the specific heat of water. So keep in mind this example here, this is a two-part example. The heat of fusion, heat of vaporization applies to this, but I thought you could handle it, and I'd just give you a two-part example right off the bat. So anyway, we're heating up the water to 100 degrees, and then this situation, as we add energy, all right, the temperature is staying the same, but we're changing it from, this would be all water, and by the time we get over here, yes, you guessed it, this would be all steam. So here we are boiling, and in order to calculate how much energy is required to boil it, we're going to use the heat equals the heat of vaporization times the amount of substance. So let's plug in. So the heat required, first of all, in order to raise the temperature, we're talking about, maybe I'll just write out the variables first. So we have Q equals mc delta T, and that will be for raising the temperature of the water. And we're going to add to it the amount of heat required to vaporize or boil all that water away. think I wrote M first. M, heat of vaporization. Oh great, what are those values? I forget. So it goes like this. The amount of heat energy is our mass, which is 0.5 kilograms. And the specific heat of water, we were using 480. Sometimes you see 4187. And then times the change in temperature. So again, the temperature is increasing by 75 degrees. That's 75 degrees Celsius, which is the same as 75 degrees Kelvin if we're talking about temperature change. And then plus, so the amount of water that we are boiling away is still 0.5 kilograms. And our heat of vaporization of water, I forget and I can't go back, so I'm sitting in front of the computer, I'm going to look it up. Heat of vaporization for water. Hopefully internet is trustworthy. I'm seeing 75.3 joules per Kelvin. It sounds believable, but I actually have the book here, so I'm going to look it up. Thank you for your patience. What page are we on? I have no idea. Aha! Okay, heat of fusion, heat of vaporization, common substances. So water, let's see, heat of vaporization, so this is saying, that's totally different, 2.26 times 10 to the 6 joules per kilogram. Oh, so that was per mole on the internet. Yeah, good lesson here in where you get your information. So, this value, we have, right, a joule is not a whole lot. So, 2.26 times 10 to the 6th. And again, this was just, when we're getting used to different quantities, it's cool to pay attention to the units, or helpful, maybe not cool, but joules per kilogram, whereas this is measured in kilograms, and so you see that the kilograms would cancel out, leaving us with units of joules, which is good, because that's what we're looking for. So let's plug this all in to our trusty calculator and see what happens. We got 0.5 times 4180 times 75 plus 0.5, and if you're calculating at home, that would be great. 2.26 times 10 to the 6, and alright, so in terms of kilojoules, well, this is what the calculator says. 1286750. And if we think about significant figures, we look at the original information presented to us, 500 grams, 25 Celsius. So it's not a ton of significant figures. So to actually say this is our answer seems a little weird. When they're big numbers like this, a lot of the times we talk about kilojoules. But let's see, 1, 2, 3, 4, 5, 6. So what if I were to say 1.3 times 10 to the 6 joules? Sounds good to me.